This is the screencast for section 6.4, example 4, choosing a base. So as you will see, we don't always have to use base E in our exponential growth or decay functions. Let's look at example 4 here. At the beginning of the summer, the population of a hive of bald-faced hornets or wasps is growing at a rate proportional to the population. Okay, wait a second. Is growing at a rate, so the derivative is proportional to the population, not time, but output population. That is a very key phrase for us. That tells us that dy dt equals k times y. In other words, the change in population is a constant times the population. So we are dealing with exponential growth. From a population of 10 on May 1st, the number of hornets grows to 50 in 30 days. If the growth continues to follow the same model, how many days after May 1st will the population reach 100? So yes, I could set this up as a y equals y sub 0 e to the negative kt problem, but instead of that, I can pick a base to make my life a little bit easier. So first of all, we already know that y equals y sub 0, and then we have a base that we're not going to call n anymore, or e anymore, we're going to call it b. And then the exponent, we're not going to call that k because that's really not the number that comes from the derivative, the coefficient of the output in the derivative. It's just another coefficient, times t. So we know that y sub 0 equals 10. The initial population is 10 wasps. Now as far as b's value, b is the rate of growth. And the problem said that the population of 10 on May 1st grew to 50 in 30 days. So that was 5 times the original amount. So I can say that my b value is 50 over 10, or 5. Now that happened not just in one day, but every 30 days. So that means our exponent here is going to be 1/30th, because it's not just every day, it's every 30 days. Which gives us the formula 100, our goal population, trying to find when it would reach 100, equals 10, the initial population, times 5, the rate of growth, to the t over 30. So, 1/30th of the growth happens on one day, 2/30ths of the growth happens on the second day, etc., until you get up to the 30 days, and that full 5 times would occur. So now we can solve this. I'm going to divide both sides by 10, and I get 10 equals 5 to the t over 30. Now, t is in our exponent, so I need to use logs. I'm going to use the log with base 5, because that is the base of my exponent. So log base 5 of 10 equals t over 30. Multiply both sides by 30, and I get about 42.920 days. I know you can't see it here, but trust me, the work using base E in this situation is a lot. It's probably about twice as much work. This was a lot simpler because we could use all of our initial information right in the setup of the equation. The now try problem number 23 says the growth of cholera bacteria. Ugh. Suppose that the cholera bacteria in a colony grows unchecked according to the law of exponential change. The colony starts with 1 bacterium and doubles in number every half hour. How many bacteria will the colony contain at the end of a 24-hour period? Ooh, okay. Well, I have initial setup of the problem. That's going to be exponential growth. So y equals my initial population 1 times the rate of growth 2, it's doubling every half hour, to the t over 0.5. And the reason why it's t over 0.5 is because it doubles every half hour, not every full hour. And t obviously stands for number of hours in this case. And then t over 0.5 is really just 2 times t, same thing. So it wants to know what the population will be at the end of a 24-hour period. So I'm going to plug 24 in for t, which is 2 to the 48th, and that means I get about 2.81 times 10 to the 14th bacterium. That's disgusting. Part B, use Part A to explain why a person who feels well in the morning may be dangerously ill by the evening, even though in an infected person, many bacteria are destroyed. Well, yeah, many may be destroyed, but look how many end up at the end of a 24-hour period. We started out with 1, and these go to 2.81 times 10 to the 14th. I don't even know what number that is. That's so huge. So clearly not that many are going to be dying off. That would be, it's just the rate of growth is way faster than the rate of the destroying of bacteria. So I'll say the bacteria are reproducing much faster than they are being destroyed, thus the population is increasing, making the person feel sick.